Hi, I'm Darren and welcome to Level Up Double E Lab. Well, I left you guys hanging last time after I finished reassembling the Viking Adventurer whether or not it would work. Well, let's find out in today's episode. Okay, it's time to test out the power supply, and I've inserted the 5U4G rectifier tube, but I've not put in the 6AG7 or the 807. I don't need those in the rig right now just to test out the DC power supply. So I've also got the dim bulb tester connected, of course. I'm using my IM13 in the background to monitor the high voltage circuit. Expect that to be around 650 volts at full line voltage. And then this multimeter here is looking at the voltage divider that is providing 350 volts to the grid of the 6AG7. And what I'll do here, since I'm using the dim bulb tester, of course, I'm going to turn it on and slowly bring up the voltage with the bulb in the circuit. So if everything goes fine as usual, I would expect the bulb not to glow brightly. But since this is a vacuum tube rectifier, I'm going to have to get the voltage up high enough to get that 6AG7, the 5U4G rather, into emission. So unlike other projects I've worked on that had solid state diodes in the power supply where you start seeing some DC power right away, I'm thinking I'm not going to see anything here until I get that bulb into, or get that tube rather, into emission. So here we go.
This item contains hazardous voltage and safety precautions must be followed. If you're following along and working on your own version, you're doing so at your own risk.
Start bringing up the voltage now. About 40 volts and nothing yet. 60 volts, nothing yet. I see some movement on the digital multimeter. About 75 volts. Oh, it's coming up now. Well, coming up a little bit, 10, 12, 20 volts. There we go. Now we can see the high voltage coming up in the background. And I do see the filaments glowing in the tube, so that's a good sign. And the dim bulb is not glowing brightly. So I'm going to keep going, bringing up around 75 volts or so, and the dim bulb is starting to glow a little bit now, and that's fine, but that's going to limit how far I can bring this up because of the resistive loss in that bulb is just dropping the voltage enough on the primary that I'm not going to get full output. So I want to pause it here for about a minute or so and just watch it and see how stable it is. So just keep an eye on it. Okay, it's been sitting here cooking for about 2 or 3 minutes. Nothing's really changed. Not seeing any magic smoke. So that's a good sign. So I think what I'm going to do now, I'm just going to ramp the voltage down, take the bulb out of the circuit, and then slowly bring it back up till I get to full line voltage. So here we go. I'll turn this down. Take the bulb out of the circuit, and then bring this up to about 125-ish. Close enough. So looking at my IM13 in the background, I'm around 620 volts or so. That's close enough also there. And 386 on that voltage divider. So that's also close enough. So this is a good sign. It looks like the DC power supply is working just fine. So I'm going to proceed to shut this down, install the other tubes, and hook up a dummy load and see what I can get in the way of output. All right, it's time to plug in an 807. I've arbitrarily selected tube number 4 from the 12 that passed all of the tests that I did back in episode number 2. Installation is easy enough, and for sure this new socket has a lot stronger grip than the old one. Can't forget to snap on the plate connection. The tube works a lot better that way. The last of the 3 tubes is the 6AG7. It also goes into a new socket and requires a bit of firm force to get it seated. And here comes the case. For testing, it's not strictly necessary that I install it, but there's no alignment or other adjustments that I need to make on the chassis, so I might as well just go ahead and put it on. Plus, it'll keep me away from the high voltage, and it does provide some RF shielding. Here it is, all put back together, including the knobs. I couldn't find a better replacement for the chicken head knob, so it stays. I decided 4 screws were enough to hold the case on. Other than cleaning, I didn't do anything to the front panel or the case. So the worn and stained paint remains worn and stained. It's part of the character of a rig this old. Now let's move on to performance testing, starting with seeing if I can get any power output on 20 and 40 meters. Alright, I've got the Adventurer all put back together, put the case on it, and the rest of the setup I have here, of course I've got the key hooked up to it and off screen. You can't really see it, but I still have my dim bulb tester connected to it just because I'm dialing down the input AC to keep it a little bit less than the 125 volt AC that's coming right out of the mains here in my shop. So I wanted to keep it a little bit lower, and I'll probably even run this on a buck transformer that I have set up for some of my older gear whenever I use it, just to keep the mains voltage down so that the filament voltages aren't too high. All right, so for the rest of the setup, of course, I'm using my MN4 just for the meter function, so I keep track of the watts output, and that's going to the dummy load on top. And to be able to hear the quality of the Morse code, CW, I should say, coming out of the transmitter, I have my home-built HF receiver here. So I've already gone through the steps according to the manual to tune it correctly. So in short, you put this switch on grid and you peak the oscillator tuning for around 5 milliamps or so on the meter. And then come over here to the amplifier tuning, and you're going to dip the plate. You're going to flip the switch to plate milliamperes, and you're going to find that dip. And everything worked immediately, no issues. Let's listen to the sound. Not much chirp there, very little drift, but the drift, of course, is going to depend on the crystal. And the one I chose has a primary tone of 7.15, I think it is. Yeah, 7.15 megahertz, which means its second overtone is 14.3. And as you can see, I'm a little bit lower than that, but that's just the nature of the crystal. Crystal is not going to be perfect. I'm driving about 25 watts or so out, so that's pretty decent. And I'll take it for as much work as I put into this and the age of the tubes and everything else. I think about 25 watts or so on 20 meters is pretty darn good. All right, I've switched over to 40 meters. I've retuned the transmitter. And since I'm using the same crystal, I do expect this transmission frequency to be around 7.15 megahertz. And it is. And it's putting out around 20 watts again. A little bit less than it was on 20 meters, but certainly acceptable considering, again, the age of the equipment and the age of the tubes. All right, I've changed the setup to take a look at the performance of the Adventurer on 80 meters. So what I've done here, I've changed to an 80 meter crystal, of course. I got a 3.707 megahertz crystal in there now. And before I started recording, I peaked the grid and dipped the plate, so it's all tuned up and ready to go. I've kept the Drake MN4 right here, so I keep an eye on what the power output looks like. And of course, the dummy load is still in circuit, but it's hidden behind everything else since I'm taking up so much room on the workbench right now. I still have my home-built receiver in the upper left-hand corner. I've set it to just over 3.707 megahertz to get a good tone quality, because crystal's not perfect. It's not exactly on frequency, so I adjusted for it in the receiver. Now what I've added is my 40 dB power tap, and I've added it because I want to take a look at the spurious emissions on 80 meters. And so I'll explain here as I go along. That's of particular interest of this Adventurer design, its performance on 80 meters. So I've got my home-built spectrum analyzer here sitting right on top of my trusty Tech 465 scope. Now it's set on XY mode so that I can use it as a nice display for my spectrum analyzer and take a look at those spurious emissions. And as a courtesy, I've included links in the description of this video to the 40 dB power tap, the home-built receiver, and the home-built spectrum analyzer. I have a whole series of videos on those if you haven't seen them before. Please check those out. I think you'll find those really interesting. But that aside, let's take a look and listen now to this guy working on 80 meters. just over 20 watts, not too much key click happening there, and I'd say that's pretty decent for a rig of this age. I moved the camera closer to the 465 so we can take a look at these spurious emissions. So let me key the transmitter, and I'll freeze it here so that we can look at what the screen is telling us. So this peak right here is the fundamental, and of course the one to the left we can ignore. That's the zero spur. It's just an artifact in my essay. So the peak to the right of the fundamental is the second, and we can see that's down about 34 dB from the fundamental. And here's the third harmonic. It's down about 54 dB. So what should it be? Well, on a transmitter of this age, we can go look up the FCC Part 97.307 for spurious emissions, and we can find that, ta-da, any transmitter that entered the market prior to January 1978 is exempt. So what does that mean? Can I just get on the air and put any spurious emission out there that I want? Well, not really, because there's a caveat there, just a best practice caveat further up in the requirement that says hams are required to reduce spurious emissions to, quote, the greatest extent possible. And of course, in that same language is a requirement that we eliminate any emissions that cause harmful interference. So what does that mean? Well, this transmitter kind of is what it is. 34 dB down is not acceptable by modern standards. In that same section, if you look and find for a modern transmitter, meaning anything built after 2003, it needs to be 43 dB or greater suppression. So if I really wanted to be a stickler and try to make this work as well as a modern rig, I need to put at least an additional, what was that, about 9 dB of attenuation on the output. Maybe an output filter could take care of that. So I think that's interesting just to know where this would rank by today's standards. I'm not sure if anyone's ever put an old Viking Adventurer on a spectrum analyzer in their hobby workshop and taken a look at it. So just interesting to see actually how it performed. I moved the camera again because I want to have the rig, the power meter, and the spurious emissions on screen all at the same time, because I'm going to talk about what exactly happens when you dip the plate current on these old tube output RF transmitters. So in simple terms, what you're doing is you're adjusting the capacitive reactance portion of the plate load circuit that's connected to the tube. And the reason you're doing that is to try to get the best impedance match from that load circuit and the tube to the load that's on the outside of the transmitter. In this case, it's a dummy load, but typically, of course, there's going to be an antenna, and that antenna might be a little variant from each time that you tune up the transmitter, and certainly hooking up a 40-meter dipole in your backyard might be different when you have a 40-meter dipole on field day. So you're wanting to tune the plate current and find that dip and get that impedance match as best as you can. The reason for doing the match, you can kind of break it down to at least three principles here. One, getting that dip is going to give you maximum output power, which we all want. We want to get the maximum output power from the transmitter. Now, there could be a caveat there. The rule can't be that simple, obviously. If you've got a transmitter that has two or more output tubes, you might need to go through a neutralization step during alignment to get that dip in plate current to align with the peak output power. In this case, there's no neutralization on the Adventurer, and the dip happens to align with peak output power. Another very important reason why you do that is you're allowing the tube to operate at its maximum efficiency, meaning you're getting the maximum power output with the least amount of input power. That's the current going into the plate. If you're outside of that region and the tube is not working efficiently, that means it's just creating a bunch of extra heat, and that's going to be very bad for the tube. You're going to degrade it over time, or worst case, you may grossly overheat the internal structure and it starts to sag and your tube goes bye-bye. So you do not want to be operating for lengthy periods of time, in some cases, depending on the tube, for more than several seconds or tens of seconds, depending on how much heat it can dissipate if you're not dipped with the power going into it. And the third reason, of course, is minimizing spurious emissions. That's why I got the 465 and the spectrum analyzer set up here. I want to show live what happens as I run through the dip, and as we'll see, as I go in and out of the dip, what happens to the output power and what happens to the spurious emissions. So here we go. Tuning it out of the dip, back into the dip. and then out of the dip. You can see those spurious emissions and the output power and the current all moving together. So that's about long enough. I don't want to key the Adventurer too much, but I think that was enough to prove the point. As I mentioned earlier, there's another reason why I set this demo up on 80 meters, and that's to talk about a notorious Newbie Gacha that exists with the design of this Adventurer. And what can happen if you don't dip the plate correctly and capture the second harmonic instead of the first harmonic of the crystal is you can end up fooling yourself thinking that you tuned the transmitter correctly, but you're actually transmitting most of your power on that second harmonic. So for example, I got the 3.707 megahertz crystal in here. If I tune it up incorrectly, I'd be dipped at 7.404 megahertz. That would be where most of the transmitter power would be coming out. Now, 7.3 is the upper limit of the 40 meter band. So if I'm transmitting at 7.404, I'm outside the band. Now, there were several online stories of some hams thinking nostalgically back when they had the Adventurer where they did exactly that and weren't aware that they were out of tune until they got some not so friendly notices in the mail from the FCC that they had done so. So it's actually very easy to do if you're not paying attention or haven't read the manual on this rig and know what you're doing. You're just capturing that second harmonic instead of the fundamental. So let me demonstrate what this looks like. So I'm tuned on the fundamental. I'm going to go out of tune and go to that second harmonic. So the current drops down, or the power drops down, then I peak right about there. So I'm mistuned. So I'm going to freeze the video here so we can take a closer look at that spectrum analyzer. Okay, so looking at this, clearly the second harmonic is much higher than the fundamental and the third, so we're definitely mistuned here. And if I had this connected to the air and just blithely transmitting, I would definitely be putting out a lot of power outside of the band for 40 meters, thinking I was transmitting on 80. Now the manual says that 80 meters is especially sensitive for this. I haven't tried it on 40 or 20 or any of the other bands just to see how easy or difficult it is to tune this up with the second harmonic. The manual also says the easiest way for avoiding this is to start with the amplifier tuning control low. There's a scale in there from 0 to 100, so you start low and increase it until you find the first dip, and that's going to be the one that you want. The out of tune one is always going to be higher on the scale, so you go lower, and that way you can stay out of trouble. Okay, and for the last test that I'm going to do on the Adventurer, let's take a look at performance on 15 meters and 10 meters. So back to the full setup here with the camera showing all the same instruments that I had for the other checks at 40 meters and 80 meters and 20 meters. I did insert a new crystal, so this one is marked so that its third harmonic apparently is 21.048 megahertz. So I went through the tuning process, and as you may notice, the coupling control, that's this guy right here, upper right hand corner of the Adventurer. You do have to adjust that according to the manual when you get into higher frequencies to try to get the best power output and overall best match. So I have tuned everything up. So let's give a listen. Again, about 20 watts, so that's pretty good. And like before, I'm going to move the camera over to the scope so we can take a closer look at those harmonics, because there's a few interesting things to see there. Here's a close-up of the spectrum analyzer results for 15 meters, and since we're working off the third harmonic, that's the signal right here. So going back to the left now, and of course ignoring that zero spur on the far left-hand side of the screen, the next two pips of interest are the fundamental. It's down about 35 dB from the third harmonic, and the second is down a little bit more, around 37 dB down. And the fourth, fifth, and sixth, well, they're down about 45 dB or more. So I'd say these results aren't too bad. You could use this setup on 15 meters and generally be not putting too many spurious emissions out there, again, for a rig of this era. All right, I've set it up and tuned it for 10 meters, and the marking on this crystal for the fourth harmonic would be 28,065. It's a little bit off, but that's the least of the concerns because we'll take a look at what the performance looks like, and it's actually not very good. So here we go. Yeah, it's only putting out about 5 watts or so. That's about the best that I could get with tuning, and again, also including the coupling control. So this really would not be a great rig in the current configuration with this crystal to use on 10 meters. And here's a zoom in for the 10 meter results, and yeah, they really are not good at all. So we're working off the 4th harmonic of the crystal, and I forgot to reset the scaling on my spectrum analyzer. Ordinarily I'd put that pip at the top, so we're just going to have to scale off of it. And if we do so, we look at the fundamental is about 30 dB down from the 4th. But look at the 2nd there, it's only about 10 dB down. So that would be really bad. You'd be transmitting quite a bit of power on that 2nd harmonic, thinking that you were just putting out power only on the 4th harmonic on 10 meters. The 3rd, it's about 32 dB down, and the ones higher than the 4th are in the 40, the one higher there is about 40 dB down, and the 5th, I'd say, or the 6th, I guess it would be at this point, it would be about 34 dB down. So all in all, this is not acceptable performance to put this kind of signal out thinking you're transmitting on 10 meters. So you'd really have to do one of two things here. I think maybe, first of all, I could try a different 807 tube. Maybe it would be a little cleaner. Not really sure if it would be until I tested it. And then the brute force method, of course, would be to make a band pass filter for 10 meters and just knock down all these unwanted side spurs here. But of course, all that energy is just going to go into heating up the filter. So really not a good solution for transmitting on 10 meters. I am really happy with how well this project turned out. This little rig holds a lot of fond memories for me, and getting it back into working condition again is an extra special accomplishment. Plus, I learned a lot about its design and operation along the way. Let's take a look at the scope of work that I showed in the first episode, starting with returning the rig to factory performance for CW operation. That I did, along with stripping it down, thoroughly cleaning it, and rebuilding it essentially from the ground up. Ditto for removing the modulation mods, they're all gone. I did decide to keep the 5U4G rectifier instead of replacing it with diodes, and the only Wireless Girl inspired mod that I made was to move the meter circuit from the plate to the cathode for safety. And I did upgrade it to 3-wire AC power, and even though I wasn't able to find a clean spot on the back to put a 3-prong socket, I did put a pretty hefty 3-wire AC power cord on it, so it's definitely good to go. And what remains now is to get it on the air and make some CW contacts, which I'll be doing in the near future. I do hope you guys enjoyed this 5-part series on restoring this Viking Adventurer. And I thank you for watching my channel and sticking with me as I go through this variety of projects that I'm interested in. So until next time, bye for now.